So there's a mystery of PDF here. So yesterday we covered this ground of the loss of statistics in high dimension as a smooth random function in very many variable, and tried to understand the topology of, so maybe that's a way to survey what we did, the topology of the landscape of this thing. And the first example was a polynomial of degree 3. I reminded you here the Kac-Rice formula, which of course is crucial, and how this Kac-Rice formula gave a link with random matrix theory. Because remember the Kac-Rice formula here, you have there a random matrix. And then discussed a bit that. Then we looked at example 1, which was precisely a random polynomial of degree p, which was simply the spherical spin glass explained here. And then I explained what we can do with this Kac-Rice approach, in particular show that this thing is exponentially complex, locate the values, the complexity as a function of the value, as a function of the index. It would be a different talk to go deeply in this, but you can recover a lot of the structure and more information even than with the usual Parisi type picture, which was what I was describing here. This picture about the low-lying states and the low temperature Gibbs measures. I even explained quickly what was happening for mixed models and give you a take-home problem here if you want to practice with the Kac-Rice formula. Needless to say, it's a hard problem, but it's interesting. So then we switched to something which is more statistical and which is a hard example, which is Tensor PCA. So quickly, that was, you're given a tensor, a P tensor, and you are given it with a noise. And so you want to recover the signal, the spike that I call V. And I described the 3 threshold, first the IT threshold, and with proper normalization, I normalized everything so that the threshold was at the signal to noise ratio 1. And so below, so that's the first question, detection. The second question was recovery. So you pick a statistical method. Here we picked MLE, maximum likelihood. And these are the questions. And the third question, of course, is computational. Can you find an algorithm to find the maximum likelihood estimator, which of course now falls into the question of optimization. And as I said, I'm interested in plain vanilla methods, both at the statistical level, nothing fancy like BP or anything like that, just maximum likelihood. And the algorithm, I also wanted to be plain vanilla, gradient descent, stochastic gradient descent, possibly online gradient descent, something like that, not something smarter than that. The analysis of dumb algorithm is usually hard. So this is what we're trying to do here. So the answers were that the detection threshold was, let's say, with the normalization 1. So below this threshold, you could not detect. There was no way to detect the fact that there is a spike. Above this threshold, then you can begin trying to do something, and we chose the MLE, and it just happened, and we discussed that yesterday, that this threshold for this statistical procedure is the same as the IT threshold, which is a surprise. I don't have an a priori proof for that. This threshold could be above 1, and in many other examples, it would be above 1. In this example, they are the same. So as soon as you can do something, you can do it with the plain vanilla method, the MLE. And then, then there is the question of statistical gap, so I didn't discuss that much. This is a paper by Reza Geisairi, Okosh Jagannath, and myself, which will appear this year in Annals of Probability, and gives the fact that when you take simple optimization algorithm like gradient descent or Langevin, SGD is not written in this paper, but then in short time, it can work only when the signal to noise ratio is larger than n to the p minus 2 over 2, which in terms of data means when m, the number of data, is larger than n to the p minus 2. Okay, so you need a huge amount of data. P is larger than 3. Okay, and if you don't have that amount of data, I explained that then you will not be able to escape. The problem is that you cannot, the drift at the equator is too weak, you cannot escape the equator, you spend too much time there, and then you end up in one of the traps of the spin glass, which is around the equator. And then you take a time, which is, we have a refutation in this paper, and so maybe in the next thing I will spend more time on the dynamics here. So, as I said, this threshold is the same as for the smart algorithm, like approximate message passing, but it's not the best that can be done. The best is to the p minus 2 over 4, and I gave some recent work that get there. When I say it's the best, it's believed to be the best. Everybody would be extremely surprised if somebody could find something that go faster, that need less data than that, but it's always possible. All right, so I explained, then we went into the proof, and the important thing was the following, is that the empirical risk was essentially a spin glass, plus a very simple thing. If you assume that V, let's say, is E1, this is just the first coordinate, U1, so this would be lambda U1 to the P, a very, very simple, the population risk is this. Okay, that's the mean, that's mean 0. So the population risk is extremely simple, it's x lambda U1, if U is the coordinate, U1 to the P. Okay, and so this population risk is very flat at the equator, all right? And to that you add the empirical risk is the population risk, this very simple population risk, plus a spin glass, all right? So then we explain what was happening. Okay, I will go faster. Again, the Kac-Rice formula was possible in this case. So let me dwell a little bit more on that again, because this will be important for today's talk. The Kac-Rice formula was possible because the Kac-Rice formula gives you a dictionary with a random matrix problem, and the random matrix problem now is the following. In this empirical risk, right, that's the smooth function you're interested in. So that's a spin glass plus this population risk. The spin glass itself has a distribution which is invariant by rotation, by the orthogonal group. So it's very natural that its Hessian will have a distribution which is invariant by the orthogonal group. So the Hessian will be a Gaussian thing, which is a Gaussian random matrix invariant by ON. It must be the GOE. And now you have this population risk which adds a spike, a rank 1 thing. So the random matrix problem you have there is a spike GOE. So it's a GOE perturbed by a rank 1 thing. And this is well understood. That's this BBP transition, long literature, this LDP problem that helped compute. And we computed the total complexity. I gave you finally a formula, and it's exponential, and we could locate where the critical points were. When the signal-to-noise ratio is too low, they are all at the equator, you have exponentially many. And when the signal-to-noise ratio increases, at some point you see a band closer to the signal. Where the complexity is 0, you don't have an exponential number, but they are close, and then the global minimum of the MLE estimator will be there. Okay, so that's what, so this is the formula that you may not want to read for complexity, and this is the complexity. So this tells you that this mean number of critical point. And this formula depends on this is the latitude and the value. And so this is this formula that you can compute using random matrix. And from there you derive everything I just said qualitatively. Okay. So enough with that, we've discussed that enough. So this is again about this question of escaping mediocrity that we discussed. And now let's go to a new question. All right, so remember the important thing here, we had the population risk, the population loss, whatever you want to call it, which was very simple. It was lambda U1 or X1 to the P. And then you added a random thing, which was like a spin glass. The important thing is that P was larger than 3, so that this X1 to the P was very flat at the equator. All right, let's take a completely different model, which is much wider. So Tensor PCA can be seen as a hard a little bit pathological example, something which is really hard to treat, but on which you can compute everything you want using random matrix. But now let's go to a really, much more plain vanilla problem of statistics. I'm looking here at generalized linear models, which are not linear. Okay? And so before explaining why they're important, let's look at the thing. We will consider these two random loss functions. So you consider here, the data is Gaussian. It's IID, I will assume very soon that they are Gaussian. You have M of them. As always, I always chose M to be capital M to be the number of data. Then you take a linear combination of this with X, a vector, in Rn, the psi in Rn. And then you have an activation function, let's say smooth, phi. Okay, think about whatever you want. And your empirical loss or whatever is this. Here. Or in the planted version, you have the same thing, but you take this minus, you have a planted signal, which I called before V, now it's X star. And you look at this difference, and you take an L2 loss. Okay? So I'm sure you recognize this thing. Of course, this can be the perceptron, if you want, right? And this is a host of statistical problems. Many, many of them are like this. So let me... So what do we do really there? Oops, what is this? Oh, this, okay, this U should have been mu. This is mu. Okay, I forgot this.
The second,
L2?
You could have used it to big C itself, right? X bar.
Yeah, but this would complicate you will see that the formulation is already hugely complicated, so, but yes, we could do that. But there I chose the simplest, really important thing where you have a planted thing. Like, to be able to compare also to Tensor PCA, because Tensor PCA also had a planted thing, right? I had one signal, okay? So, here, okay, so what's happening? You have M data, we'll assume that M, of course, is alpha n, as always, alpha larger than 1 for obvious reasons. And then what you have access to is this, you observe the phi of psi mu inner product with X star, right? That's what you expect. And so this generalizes standard linear regression, right? If phi is linear, this is regression. So these two random loss functions cover, very well-studied estimation problem, depending on phi. So of course, when you have L1, it's close to the perceptron, but for L2, you would have linear regression when phi is linear, phase retrieval when phi is quadratic. We've seen an example like that for compressed sensing. We've seen logistic regression yesterday, which is of course of this form too. And GLM is this general thing. It was introduced by these two statisticians in '72. If you look at the Wikipedia article about them, because this is a big thing, you will see in the notes that I think it's Wedderburn, who said that his only regret is to have called that generalized linear model. Because of course they are not linear, and he thought by saying generalized linear means non-linear. But okay. And then of course, as we've seen, the teacher-student network, or what is also the one-node network, so you have many, many things there, all right? So suddenly we move from a kind of one example of Tensor PCA to something which is much broader, but I hope to convey that the lessons we learn for Tensor PCA, or maybe for the more general model that I call P plus K, go here, right? P plus K model has an advantage, it's because you are in the world of GOE, which is way simpler than the world of random matrices that we'll have here. Okay, so let's see what there's too much of a literature on that, but if you just want to have a recent paper which is close to this community, this paper by Florent, Lenka, Barbier, Macris, and Leo Miolan last year, or the year before, is nice and gives lots of references, okay? But in the last few days, you've seen many references to all sorts of different problems related to that. Okay, so I think I don't need to convince that this is an important problem. Now we are really in the world of statistics. We are not yet in the world of machine learning. Okay, so of course the questions we had the question one, of course there would be another question, which is the IT threshold. I will not go there. Now question one, because we are already, when you do that, you have already chosen your statistical method. You have your loss function, right? So the only question you have now are the last two questions. So first, what is the complexity of this function? Are these complicated things or not? So this is a joint work with Giulio Biroli and Antoine Maillard that has been posted less than a month ago. And there's an upcoming, so this is a work at the level of physics, so there are plenty of replica and things like that. And then there is, but there's a rigorous part too. And then there will be an upcoming work where we'll give a much more mathematical version of it. Okay, but I'm sure you can trust the results of this one. Okay, so the question two is, once you understand the topology of this landscape, is how hard it is to explore this landscape, how hard it is to find a minimum, let's say in reasonable short time. Again, with plain vanilla algorithm, GD, SGD, OGD. OGD means online gradient descent. Initialized randomly. By that I mean with no prior knowledge. Right? You remember my picture of the sphere with the two little hemispheres? You're not starting in one of those little corners of the universe. You don't know anything, okay? So you may have the problem of escaping mediocrity in this problem too. So this is current work, which will be online soon by Reza Geisari, Uko Jagannath, and myself. The first work to come out will be on OGD, because the work on OGD is simpler to analyze. All right. So, by the way, let's come back to the definition of the function. Where are they? Here. I'm sure you can see that these functions are not always complex. Right? Look at this one. Take phi to be linear. Not very complex, right? Because then the function itself is linear. So a linear function, and again, I will assume, just to simplify that, and to be able to compare to Tensor PCA, I will assume that my prior is just x, the spike I will try to find, the x star if you want, or the x here, are unit vectors, and I know nothing about them. Right? So my prior is x is on the uniform measure on the sphere. I could do that, and we are also doing it on Rn, or other manifolds, but let's stay on the sphere. Of course, you could also do that with different priors. You could have some prior. You could know sparsity or things like that. I'm not doing it now. Okay, so if you take now a linear function, if phi is linear, you take a linear function on the sphere, how many critical points? We've already answered this question. 2, right? So you take the function x1 on the sphere. There's the south pole, the north pole, this is a minimum, this is a maximum, and that's all you have. That corresponds, remember in my tensor PCA, that corresponds to p equal 1. A 1 tensor. Easy. Right? So that cannot be complex. We have to find that in the proofs. If phi is quadratic, then this whole thing is quadratic in x. Again, a quadratic function on the sphere cannot be exponentially complex. The maximum number of critical points for a quadratic form on the sphere is 2 times the dimension, twice the dimension, right? Because you just look at the eigenvectors and plus and minus, and that's it. So it's diverged linearly with the dimension, not exponentially, right? So if phi is quadratic, this cannot be exponentially complex, right? Okay? So this here, you have a little shift because you have this square here, but obviously, you have the same thing. If phi is linear, this cannot be exponentially complex. So, what are these? I mean, it's clear that we have to feel that in the study. Okay, so let's go back to this.
Can I ask a question?
Sure, please do.
L1 was the loss. That was the average of fees.
I'm sorry.
L1 was the loss. That was the average of fees. L2 was...
No, there are two different loss functions. We are studying both. The really important one for statistics is L2. Okay. But I study L1 just to compare to the known results with perceptron.
Yeah, so the L2 is the quadratic loss
yes.
with respect to the targets, right?
Yes. L2 is quadratic loss with respect to the target, exactly. You have access to the phi, this nonlinear activation thing, of the inner product of the data with X, and you just do an L2 loss. Okay? So think of L2 if you want to think of usual statistics problems. Think of L1 if you're a physicist and you know more about the perceptron. Okay, that's why I present both at the same time. Okay, so under natural assumption, smoothness of the activation function, and we will forget about that. We can, of course, we don't forget that in the paper, but we can compute the complexity of these two functions. In the high dimensional setting, again, when n and m are large, and their ratio converging to alpha. So m is alpha n. Okay? And we assume that the data is Gaussian. And the method, of course, is to try to use, to study complexity, is to try to use Kac-Rice again. So it's a simple extension. In fact, here, Kac-Rice, as it's usually stated, is for Gaussian fields. Here, this thing is not Gaussian, but it's a function of a Gaussian. You can work around this. And in fact, it is done, and I mentioned two books about Kac-Rice, and in this book, there's a little appendix somewhere which does something similar, and so it's not a big surprise. Okay, so you can extend Kac-Rice, just take it for granted. The formula I gave you is valid. So now you can ask yourself, what is, oh, interesting, so something is, okay, whatever. So what is the natural random matrix theory question that this brings, right? So it should be no surprise that the random matrix question that comes up is not the GOE, we don't have the invariance by rotation, but the Wishart case. So let me remind you, I imagine that everybody has some grasp of random matrix theory. But so what are the results known in random matrix? Right, let's just start afresh. You have, so of course you have all, okay, what is a random matrix problem? You take, let's say, a real symmetric or complex Hermitian matrix n by n will be large. You want to understand the spectrum and maybe the eigenvectors if you're ambitious. Okay? So, and then when you understand the spectrum, you can understand it at different levels. You can understand the bulk, you can understand it at a small scale, at the smallest possible scale, you can understand the edge, all that is well known. But all that is well known for only two classes. Random matrix is very, very narrow. And the whole talk about universality is cool, but hides the fact that we know very, very little in random matrix. There are two examples in random matrix, and that's it. There's the GOE, or GUE, and then there is the Wishart matrices. Okay? By the way, random matrix is not a physics invention. It is not Wigner. It was created 24 years before by Wishart in statistics, back there, right? So the spectrum of a large random matrix has first been studied by Wishart in 28. So these are the two examples. And then generalization of that. You have the invariant ensembles that have been studied in physics for a long time. Then the recent results in math about universality, for instance, in the case of Wigner matrices, where you take now, let's say, real symmetric, and when you take the entries to be IID, but not Gaussian. Right? And then there's a lot of work in the last 10, 50 years to go to very precise results showing that then the behavior of the spectrum is essentially, even at very small scales, the same as for Gaussian case. Right? So why is Gaussian useful? It's because of the GOE. When it's Gaussian, you can compute explicitly the distribution of the spectrum. Same thing for Wishart. And this is what Wishart did in 28. And then you have the generalization for Wishart, and same thing, universality, but they're the only two cases. And that's it. So for instance, I was mentioning that it would be useful to have Gaussian matrices with correlated entries. And there are only recently very few results in this direction. And interestingly, physics has not studied this systematically, or math either, in fact. And it's hard, it's really hard. But so that's why I'm taking those two examples, those two classes. This class falls in the other large class of random matrix, which is Wishart. So what is a Wishart matrix? Do I need to explain the random matrix side of this? Maybe? Okay, so. So that's the other example of random matrices. Take, I don't know, Z, a large Gaussian matrix to begin with. And, or for, let's say, so Z is of dimension, I don't know, m by n. okay? It depends how you put my data, no, maybe you want to put the data in column, right? So these are your data, each column of size n is a data point, and you have m of them. If you want to understand typically the covariance matrix of this, you would do this. Transpose, and maybe divide by m or m. And again, you assume that m and n are proportional. Right? So that's what Wishart did. You take this random matrix, and you want to understand, for the moment it's a very simple, let's say these guys are standard Gaussian. You know, of course, if you were in a situation where m, let's say, was, the n was fixed and m was large, so you had, let's say, dimension 3 vectors and a very large number of them, this thing would, of course, this is the empirical covariance, this would converge to identity, right? But when m and n are the same size, this is not identity. And what you find when you look at the spectrum of this, you have a formula for it, which when alpha is larger than 1 looks like this. The spectrum looks like that. Okay? That's the Wishart distribution, which depends on alpha. Okay? So that depends on alpha, which is the ratio of m and n. Okay, well, of course, when alpha is smaller than 1, you get an atom at 0. Okay, so this thing replaces the Wishart distribution, replaces the semicircle that you probably know for the GOE. That's the bulk. And you have the same kind of results for this. You understand the distribution of the spacings. You understand the distribution of the top eigenvalue, the bottom eigenvalue, which are what are called traceoidem. You know a lot, all right? So that's one thing. There's one peak, which is essentially around 1. So if you let alpha go to whatever it was, infinity, you have very, very much data, then this thing will concentrate on the Dirac mass at 1. Okay? Naturally. Okay. Because again, if m was very large and n was finite, this is the usual setting where, of course, this sample covariance matrix was converged to the covariance matrix, which is the identity. So the spectrum would be all 1. Okay, that's the trivial case. But now what about if your covariance, the true covariance matrix is not the identity? Right? Then it's the same problem, but except that in the middle you would have a diagonal. It's exactly the same algebraically. If Z is a Gaussian vector, which is not, whose covariance is not the identity, then you can write it as a matrix time a standard 1, and the spectrum would be given by this, right? So, and this D would be a diagonal matrix. So let's say, just to simplify, just so that I can draw a picture, that let's say that this diagonal, which are the variances of your Z's, take 2 values, 1 and 5, 1 and 4. So if you had alpha very large, you would have 2 Dirac masses, one at 1 and one at 4, right? But when you take alpha not infinite, you would get a mixture of things like this. So, right? But then, when alpha is too small, these two can begin to merge. You can have something like this, for instance, right? So this limiting distribution is well understood and exists. What you need is that the empirical, the distribution of the value, let me call di, the values of the diagonal. D is the diagonal of di's. If the empirical value, the empirical spectrum of this diagonal, which are just the empirical values on the diagonal, if this converges to a certain distribution, I don't know, rho, then the spectrum of this converges to a distribution which depends on rho, which I drew here, right? So when rho is the Dirac mass at 1, it's the standard Wishart. When rho is something else, it's something else, okay? And this is well understood, all right? Very interesting things can happen here because you see, which are more difficult to get, for instance, in a GOE case. For instance, what happened when these two things touch? The statistics here are different. They are no longer traceoidem. They are called pure C. I mean, this is a whole world of random matrices. Okay? So this is the basic fact. If the spectrum of the diagonal converges to something, the spectrum of the empirical, So let me put it differently. What is the diagonal? It's the spectrum of the diagonal is the spectrum of the true covariance matrix. If the spectrum of the true covariance matrix converges to something, then the spectrum of the empirical covariance matrix converges to something. And the something is the Wishart distribution associated with this rho. I don't describe it precisely, but that is well understood.
So the first one is for when TIs are randomly chosen between 1 and 4.
No, you don't need them to be random. You just need the empirical spectrum to converge. So for instance, you could have half of them, let's say here maybe I put, I don't know, 40% are 1 and 60% are 4, right? And then this gives you... It's just the fraction, the limiting measure that you obtain here. But this limiting measure could converge to something continuous. Rho could be a continuous distribution, and then you would still have this thing. Okay, this is very, very related to a very interesting part of mathematics, which is called free probability, okay? Non-commutative free probability. And this has what is the reason you have these two things? It's just, why is it, you could ask yourself, why is it that random matrix has only these two classes of examples, right? This is sobering, right? We've worked on this for a very long time, and all the things we can do are in these two classes. Not all of them, we can do more, but these are the natural ones. Okay, there's another situation like that in probability. I'm sure you know. Where every limit theorem is either this or that. What are the limit theorems you know in probability? Law of large number, okay, no fluctuation, but for fluctuations, you know essentially only two. One is the Gaussian case for sums of random IID random variables, and the other is the stable distributions, right? And so when you do a sum of IID random variable, if it has a second moment, converges to Gaussian. If it doesn't have a second moment, it has a heavy tail with a power alpha, it converges to a stable distribution, right? And that's it. That's the only theorem you have. And in fact, in this case, you can prove that there are no other theorems. That's the only one that you can have for sums of IID random variables. So it looks a little like that. And in fact, it is exactly like that. If I don't have time for that, but if you understood what free probability is, these two things correspond to what is a free convolution, like sums of IID in this non-commutative context, and they correspond to the Gaussian and stable case. Right? So in some sense, it's natural that we have found in examples only these cases for the moment. All right. So with this in mind, let's go back to this. Yeah. All right. So the random matrix that you find in this generalized statistics model, linear model, of this form. Generalized Wishart, x, d, x star, where d is diagonal. I call it z over there, but now it's x here. And x is random Gaussian with IID entrance. So that's exactly the model. So everything is contained, information is in D and in alpha, as I said over there, right? So the spectrum, as I just explained quickly, is well understood. When the empirical measure of the entries of the diagonal converge, say to a measure nu, I called it rho over there, okay? And as I said, it's linked to free probability. It converges to what is called the multiplicative convolution of the asymptotic spectral measure nu, and the Marchenko-Pastur distribution with ratio alpha. Okay? So what I'm saying is that this distribution here is in fact this multiplicative free convolution of the usual Wishart and rho, whatever that means. Okay? But now it's not enough, because what we have is that our thing is our H, the Hessian, like before, this would have been the GOE. But now on top of the GOE, we had a spike. So here we have to understand the rank 1 perturbation, or rank 2, or rank 17 if your signal is larger, finite rank perturbation of this Wishart matrices. Okay? Because remember, the spike induced, like in the Tensor PCA, induced something in the Hessian. All right, so in fact, this BBP transition business in 2005, the first paper by Mike Pesce and myself was, in fact, not on the GOE, but on Wishart cases. Okay, so in fact, in statistics, this is the perfectly natural thing to do. Right? This is all right. So what do we get? We can compute complexity for the two function L1 and L2. And we compute the limiting annealed complexity in terms of a very complicated variational principle. And we can also compute the quench complexity using this non-rigorous replica approach that we introduced with Giulio, Valentina, and Chiara in the case of Tensor PCA. One word about this. Of course, I'm dissing the replica method, but it's really nice. So in this case, the replica method, this replicated Kac-Rice that was essentially found by Valentina here, Ross, is much easier to swallow and much simpler than the usual replica method. Okay, so this one is kind of acceptable for me, right? So I encourage you, if you want to learn that, to go there. At this point, we didn't write the complexity. We compute the complexity of all critical points, not with a fixed index, but this will come soon. Okay, as before, we needed an LDP, a large deviation principle, for the spiked eigenvalue. That was before for the GOE, proven by Maida 10, 12 years ago. So with this, you can understand the complexity of local minimum. All right, so let's go for the result. What is happening here? Okay, so here's the result. We compute again, so let's take B a subset of the real line. We look at the number of critical points. So first I start with L1, the perceptron-like thing. So number of critical points with values in B. 1 over n log, this is the annealed complexity. 1 over n log of the mean number of critical points with values in B is obtained as a variational problem. By the way, the formula I gave you for the GOE was also obtained by a variational problem, but one you could solve. This is where you had a very explicit mess, okay? But here, this one is more interesting. So it's the soup over all the probability measures nu, such that the integral against phi is in B, of T1 nu minus alpha h nu, is here this h of nu is the relative entropy with respect to the standard Gaussian measure, so it's a simple thing. And alpha is the ratio of M and N. And T1 is a rather involved function on the space of probability measures that I describe here. So first there's a constant, no big deal, minus 1/2 log of the integral of phi prime, this is the activation square against d nu, plus k1 nu. So all these two terms are easy to look at, right? This is a moment of, this is the integral of f phi prime square against d nu. All right, but what is K1 nu? K1 nu is a logarithmic potential. So you all know what the logarithmic potential of a measure is, right? So, it solves, Laplacian u equals mu. But, so here it's a logarithmic potential in dimension 2, that we have a log. So here it is. So this is a logarithmic potential. It's the integral of log, absolute value of x minus something, z, let's say, against the measure. So that's the logarithmic potential of the measure, mu nu, taken at this value. All right? So what is this measure? Mu nu, it's a complicated guy. It's the free multiplicative convolution of the alpha Marchenko-Pastor distribution with the image of nu by the map phi second. I don't expect you to swallow that very fast, but it's perfectly described. It's there. Okay? So just notice, if phi is linear, what is phi second? 0, right? So the map of nu by the map 0 is just Dirac mass at 0. The Marchenko-Pastor, the free multiplicative is blah, blah, blah. This is the Wishart distribution. Okay, and now this guy is easy to see what it is, okay? Good. So it's a big mess, but it's what it is. So using just the kind of reasoning I started, you want first to have a sanity check that if phi is linear or quadratic, in fact, this complexity vanishes, and it does. All right? So for L1, and that's well known. Again, it's well known because if you go back to the formula giving you L1, you see that if phi is linear or quadratic, L1 will be linear or quadratic, so it will not have complexity. So this case corresponds again in the tensor PCA case to p equal 1 or p equal 2, right? The easy cases. So you find it again. Now, for what activation are these model complex and how to compute this complexity, now this question is reduced to this deep variational problem, right? So find this thing. This is super hard, so we can do that only on a few examples, but it's very interesting because it tells you, I give you a phi, and you tell me with this phi, that's the only thing which is hidden. Let's go back to the formula, which is admittedly a little complicated, but everything only depends on phi here, the activation function. You have an alpha, of course. You have here phi prime, alpha, and then this thing you have phi prime, and this is, whatever it is defined by phi, right? So when you change phi, you change this whole T, you change the variational problem, and the question is, for what phi will this complexity be exponentially complex? So this gives you an exact characterization. It's complex if and only if this. All right? And as I said, linear or quadratic is not complex. Okay, let's go now for L2, which is the more statistical thing. I started with L1 because first it's linked to the perceptron, and second, it kind of gives us the flavor for L2, where the formula is way more painful even. So here it's more painful because we want more information. Why do we want more information? It's exactly like for the tensor PCA. Remember, we wanted to understand complexity, but we wanted to understand complexity as a function of latitude. We wanted to be able to say that our critical points are close to the signal or not. So we have to add one variable. Remember in the formula I gave you for tensor PCA, we had the latitude. Right? So here we have to put the latitude. So the latitude here, instead of being called M, here, oops, it's called Q. So if I take a subset of the real line, that will be for the values as before, Q a subset of the interval, and I look at the number of critical points of the function L2, where, let's say X of the function L2, where the value is in B, L2 of X is in B, and where the overlap with the signal is in Q. So that's the latitude. X star is fixed in Q. Right? So the parameter Q is about the latitude, the correlation with the signal. All right. And so the formula is this, very similar. The annealed complexity, oh, I forgot a Q here, is a soup for Q in Q, or the soup for nu in the set here of T2 minus alpha, the relative entropy. So it's very similar, except we have this extra soup, which is natural because it's linked to the fact that I've added one variable, the overlap. So T2 now is a really involved functional on the space of probability measures on R2. Now I need probability measures on R2 because I need two things, the value and the overlap. And this set of constraint here is a set of probabilities on R2, which depends on B and Q. Okay, so let me explain this. So, okay, heavy notation. Let me define phi q to be the activation function, the function of two variables now, qx plus square root of 1 minus q square y minus phi of x. The set of constraint is the set of probability measures that satisfies these two things. This thing should be 0, this integral should be 0, this integral of this thing square should be in B. Right? This guy represents the value, this guy, okay? Now, the functional T2 is given by this thing. So you optimize this on this constraint set. So we have the same extensive factor here, 1 plus log alpha over 2. We have something that looked very similar to what we had before, an integral minus 1/2 log of an integral, now against this distribution in two variable. Again, all that is entirely defined by phi. It's a more complicated integral, but it's very similar. And then we have again a K2. The K2 is again a logarithmic potential, log of absolute value of x minus something against a certain measure. This measure depends on alpha, phi, q, and nu. And the measure is in fact given, now we are back here, it's given by the asymptotic spectral measure of this Wishart matrix. Okay, so we are exactly there. Okay, this is a special Wishart matrix. When Z is standard Gaussian, and when why does it do that? Okay. Where the diagonal is a diagonal matrix made of IID entries. Here the Y mu are IID distributed under nu, and the function FQ is whatever it is as defined by phi. Remember, nu is something we are optimizing on, right? Our variational problem is on nu. Okay? So that's where it is. So this thing here, so let me walk you back. You have this y mu, which are IID distributed as IID under the distribution mu. You take this functional FQ of it, build a diagonal matrix. From this, you build this Wishart matrix. You look at its spectral measure, and this is mu. Right? This is also, I didn't describe it here as a free convolution, but it can be seen as a free convolution too. Okay. And the limiting measure is this. The asymptotic spectral measure of this guy is this thing here. Okay? And so of course it depends on Q because this F depends on Q. It depends on nu because the distribution of the Y depends on nu. It depends on alpha and phi because alpha and phi are hidden in all the formula. Okay, so if we walk this back, we have this measured mu. Now we have a T, which I also must have written somewhere. Here. Okay, which is a big mess, but still only defined by phi. And so now you have to understand how you minimize this. Right? So just a word about that. So again, you can test. Let's take phi linear, just to do something trivial. Then if you take phi linear, all this will be completely trivial, and you will find the functional that the complexity will be zero. So the real question is, how do you minimize the logarithmic potential? Right? What is? How do you understand? Here you have a moment. The structure of the two problems are something like this. You want to minimize the integral of some function against a measure minus some form of logarithmic potential of nu, right? So how do you do that normally? What is the minimizer of a logarithmic potential when you have this? One way to do it is to ask the question, what is the logarithmic potential when you fix the moment, right? That is well understood in potential theory. The problem here is that it's not the logarithmic potential of nu. It's a logarithmic potential of a complex mess built from nu, right? So this problem is really much harder, okay? But the complexity is computed, all right? So, and of course you can, so let me explain now quickly, but maybe with the computation rather than, how can you try to relate this, at least mentally, to what we were doing with Tensor PCA, okay? So to compare with Tensor PCA, I will look at L2, the case where you have a signal, okay? So remember what L2 was, it was 1 over m or something, sum over of my phi, of psi, oh no, I call them mu, I'm sorry. Mu, psi mu dot x minus phi of psi mu dot x star, the signal square, right? And we had the same picture, so let me draw again this picture of, we're on the sphere, again, we could do that on our end, and let's put my signal x star again at the North Pole here, okay? So that's the thing we are looking at. It doesn't look much like the loss function, the MLE for Tensor PCA, right? But in fact, we could do it. Remember the structure for Tensor PCA, where the function we wanted to optimize was lambda x1 to the p, the population risk, plus the spin glass. all right? But here, it's not written like that, but you could. You could simply write it as you take the expectation of L2 of x, right? The true loss function, the population loss, plus L2 minus its expectation. No big deal at this stage. Right? I've done nothing. Let me give a name to this. I don't know, population risk, psi of x. Okay? This, for tensor PCA, was x1 to the p. If x1 is the coordinate, let me call this vector e1, so that x1 is the coordinate in this direction. Right? That was x1 to the p. And that was spin glass, a p spin glass. All right? In the P plus K model, which we invented, this was a P spin glass, and this was when x1 to the K, so that we could play with the two parameters. All right? So what is this? Can we compute this? There is a very neat trick that we found after this paper with Reza and Okosh, which tell you how to do that. This is a very simple computation. The expectation of this, of course, when you take the expectation of L2, you can forget about the sum. It's just the expectation of this square, right? So that's the expectation of phi of psi mu x minus phi of psi mu x star square, right? That's what we have to compute. So here's an interesting lemma, which is neat. You take the activation function, which I called phi, and you decompose it. Phi is in L2. Let's assume, because that's not much of an assumption, that phi is in L2 of the standard Gaussian. Let me call it gamma. Right? So phi is in L2 of the standard Gaussian on the line, right? Which is perfectly okay with all the phi you know. Right? Because to not be in L2, you have to grow fast at infinity. Okay? So let's assume that if it's in L2 of gamma, then you can of course decompose it into, on the orthogonal basis of L2 of gamma, which is the best in the world, which is the Hermite polynomials, right? Right, L2 of gamma has an orthonormal basis, which is the Hermite polynomials. So what are the Hermite polynomials? You just start with the polynomials, 1x, x2, x cubed, etc., and then you orthonormalize them for the L2. So the first one is 1, the second one is x, the third one is x squared minus 1, etc. Okay? And so you can always do that. And in this basis, this becomes very easy to compute. It's sum 1 to infinity of uk squared, the coordinate, times mk minus 1 square, where mk is, in fact, simply what I would call I don't know why you call it. No, it's not mk, it's m to the k, where m is in fact x1 with my coordinate over there. So I should just write x1 with this coordinate. M was, before was the latitude, so here it would be x1. Okay? So when this is a beautiful formula. Okay? Exercise, do it. Once I tell you it's true, everybody can find the formula. The nice thing now is, so of course it starts at 1 because adding a constant to phi, the first coordinate on h0 is a constant. Adding a constant to phi doesn't change this, right? Because it's phi minus phi. So clearly this will not depend on the first coordinate, and then you have this. But now, let's look at what this means. We have, so this is my population function, which used to be x1 to the k. Now it's like entire series in x1s. But the question is, when do you have a component on the first thing or on the second thing, right? Which was like before. Before tensor PCA was complicated because because this loss function was very flat at x1 equals 0. It started at x1 cube. So this starts at x1 cube if the first two coordinates are 0. So you have different classes. If u1 is non-zero, that's one class. And then you have another class where u1 is 0 and u2 is non-zero. And then you have a third class where u3 is non-zero. Or whatever, uk is non-zero for a k, the first for a k larger than 3. All right? This corresponds exactly to what we have for the tensor PCA case. This is p equal 1, p equal 2, p larger than 3. All right? And of course, then you have to understand that this thing here, which was the spin glass, now it's also a spin glass thing, which may not be very complex, but much more difficult to analyze than the usual orthogonally invariant spin glass that we have for the p-spin model, right? But this is now this term is the spin glass, this is the population, and it has exactly the same structure, and we have 3 classes. So if you admit this picture about complexity, because I'm not going to give the proof, what can we expect about optimization, right? You should expect again that if you take a point at random and you apply gradient descent, Langevin, or online gradient descent, stochastic gradient descent, whatever, the real problem will be that your gradient will again be very weak here if you're in case 3. Exactly for the same reason. But not weak at all in the case 1 or kind of critical in case 2. Okay? So what's going on here is that indeed, and I will give more serious results next time, if you're in case 1, so case 1, why is it easy? If when u1 is non-zero, you have a term like x1. So the gradient is non-zero at the equator. The gradient is not 0, it's easy to escape. Case 2, the gradient is 0, but its derivative is non-zero. So by just waiting a little bit, you can count on it. Case 3, harder. Okay, so in case 1, you should expect that you can learn. So let me state the result, which is a result now, in the case of online gradient descent. So online gradient descent means I do the simplest thing there is, the really plain vanilla thing. I take my L2 function, and I take a new sample every time, right? And I just follow the gradient defined by this new thing, online. Never, I don't have batches, I don't reuse, what?
Without repetition.
No repetition. So that's, of course, that's what you want to analyze first. So you do that. And if you do that, you ask yourself, so I have M data here. You do that for your M steps. And you ask yourself, after my M steps, have I correlated with the signal? Or am I still in the mess? Am I still in the mediocrity? Right? So the answer will be yes, in case 1. As soon as alpha is larger than a constant, and other smoothest, also we have 4, we're mathematicians, so 4 precise conditions, but that are satisfied in this case. Okay? If you, so the take-home message is, as soon as alpha is larger than a constant, which means your number of data is, I don't know, larger than 3 times n, then after your m data, you have correlated with the signal. Okay? You haven't correlated perfectly. You are not at the signal. But if alpha tends to infinity, then you will. Okay? Like before. Remember in the tensor PCA, you had this thing that was going like that. Okay? If alpha is critical, that is, not alpha, I'm sorry. If you are in the critical case, where u1 is 0 but u2 is non-zero, then you are like in the k equal 2 case of the p plus k model. And what we prove, and it seems optimal, I'm not sure, I cannot put my hand in the fire for it, but we believe it's optimal. It works after m iteration, But now when alpha diverges slightly, that is, you cannot do it with m equals alpha n. Your number of data, again, has to diverge, but like log n square, the ratio. M has to be like n log n square. We are fighting hard to have log n, but who cares? Okay, so it diverges exactly like I predicted. It's a critical model. For critical model, you just need a little bit more of data than the dimension. Okay? And in the case 3, then your alpha, the alpha you need, is our old friend, n to the k minus 2. So if you remember, in Tensor PCA, the signal-to-noise ratio you needed was n to the k minus 2 over 2. But that, by natural scaling, corresponds to the data m to be n to the k minus 2. In fact, with this, with online gradient, we can do even better, because what we have for Tensor PCA, we needed m to be strictly much larger than n to the k minus 2 over 2. Right? Here, it has to be a constant, we can prove that with a constant times n to the k minus 2 over 2, it works. So we are in the same situation. As soon as you're in case 3, the population risk is too flat. And remember, I'm not talking about complexity here. I'm talking about escaping mediocrity. It's too flat. Complexity will play the same role. We haven't proved it, but it will play the same role. I'll come back to that. It's too flat, and then the time to escape, it will be finite only if you have very much data. N and exactly n to the k minus 2. The same threshold that the one that was obtained for AMP in the Tensor PCA. I haven't checked, but I'm sure that AMP will not beat this threshold. It's the natural threshold. And then, of course, now you can ask yourself, can we beat this threshold with SOS or Kikuchi or all this fancy new stuff? But for plain vanilla algorithms, this is what you get here too. So I will try to explain. So for the moment, we have that for online gradient descent. We have it for gradient descent. It's an enormously more complicated mess. We haven't yet studied the case of SGD with repetition and all that, but honestly, I'm tired. Why would you study that when it works here and there? So somewhere in the middle, it must be true too, right? And this is for somebody else to do. But so I believe that this dictionary is correct. And so the important models are the critical models. The supercritical models, forget it. They are like Tensor PCA. They are hard. You can't do anything. You need an enormous number of data. You have to be Google, right? Because then you have access to the... If the problem is that hard, the only way to solve it is through huge data. But the interesting one where you have something to do are the critical ones, right? And the easy one, everybody can solve them because you have nothing to do. Okay, so it's exactly the same picture. So this is, for these guys, and it's, so for instance, one node network type things. It would be very interesting to do for 2 node networks, 3, not 2 node, 2 layers. That I'm not tired, that we will try, okay? Because at some point it's
This trick should work there also.
What?
This trick will work for 2
I don't know, but probably yes. This is a super nice trick of which I'm extremely proud, which took 1 minute, but because suddenly everything became clear. This is what makes the parallel between Tensor PCA and this, right?
Yes, yeah, because if you have 2 layers, you don't need to worry about k equal to 3, for instance. You could be happy with k equal to 2.
Yeah. No, but that's exactly the point. I imagine, here's my wild conjecture of a mathematician. The good networks, the ones that work well, are critical. Nobody will try something with, except if you're Google. Then in your first phases, you may go to huge data because you understand nothing, and then you choose your network, which is here choosing phi in a better way, adapted to the data, right?
To add another sentence to that comment, linear like nonlinearities work well, positively homogeneous nonlinearities work well, but it's not as if exponential nonlinearities do not work.
Yeah.
Or are hard. They work. So what k equal to 3 really suggests is that there are terms in the nonlinearity expansion which are more than x squared.
Yeah.
But in practice, x to the 4 works also. This is just an empirical.
On this GLM things, you've tried that? For neural networks, I don't, I'm a mathematician. I told you what I believe, but the algebra could be much more complicated. I don't know. But this is for GLM, this is what will happen. So what is the role of complexity, which I just described? Is the same as for Tensor PCA. That is, if indeed you have complexity, and you will have near the equator, then if you are in this case there, where you can't escape, you take a very long time to escape, then you explore the equator long enough to find the glass phase. It's the same thing. And then you're dead. And then it takes a very long time, exponential, whatever. So then it's over. So it's the same thing. But in the first two cases, even if the equator were to be complex, you don't really care because you just zoom out. It's the same thing for the P plus K model. If you take this P plus K model, if K is smaller than 2, then you don't care. You have the complexity of a P-spin at the equator. It is there, the glass phase is there, but you don't give a damn about it because the gradient is so strong that you just zoom out very quickly and you don't find at all one of those spurious minima. You don't see them because you are pushed out. Again, to find these, you have exponentially many minima, but they take time to find. They are not like that. So, in fact, if you zoom very quickly in one direction, you have very, very small chances to find them. So it's the same thing here. You may or may not have complexity at the equator. In case 1 and 2, that doesn't really matter. In case 3, this is what kills you. Okay? Then there's another question, which I have now no clue, but you could also have complexity in the region where you come, at the end of your trajectory, right? You're coming up, you will end up somewhere here. So as I explained in the Tensor PCA, in this region, the complexity was 0. But in the P plus K model, you have cases of P and K where the complexity could be exponentially positive here too. So then it would mean that when your trajectory has escaped and arrives here, again, now you meet this glassy phase and all that. But it's not that crucial, because what does it do? If the true maximum the thing you want to optimize, to find is here, and you have complexity in the band like this, and when coming here, you find you get stuck there, okay, you lose a little bit, but in terms of performance, but who cares? You don't want to continue your algorithm because it will take exponentially long. Right? So there is a possibility of seeing complexity at the end of the trajectory in both cases, Tensor PCA and here, P plus K and here, but that's not that crucial at this point, right? And this problem is easily solved because if you increase a little bit your alpha, you move this thing up, right? So that's not a big deal. So by just multiplying the size of your data by 2, you move up. Right? So so next time, and I will stop here, next time I will explain this online gradient descent thing and just allude to the cases of gradient flow and all that. Okay?
Complexity has been calculated for this problem also?
I'm sorry?
Complexity has been calculated for this?
This is what I just showed you.
No, you're basically...
No, I gave you I give you the formula for a general phi of the complexity for L2. And as you've looked at it, what I could guarantee is that linear or quadratic, no complexity, which means case 1 and 2, no complexity. Case 3, for what cases will you have complexity and where will the complexity be? I don't know. This is we have to solve this variational problem. And again, it depends on phi. So the important thing would not be because the question I'm asking myself, or that you are asking me now, is an adversarial question, right? It's like, build a phi that will be horrible, right? That's not what you want to do. You want to take one of the phis that are natural and see if they are complex or not. And that we haven't solved the problem. This will come. This is fresh, so this will come. Okay, thank you.